Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth. We are adding a video into this AP Physics 1, Unit 1 Kinematics. We had this student with an excellent comment that said, hey, listen, you talked about how a projectile takes off and lands at the same height, but what if it doesn't? How do I do that problem? Excellent question. Shout out to you. And today we will be addressing that. All right. We're going to look at an object that is shot from a cliff at the top of the cliff, so it's not taking off and landing at the same height. Before we get started, though, just really quickly, we need to review some things about if it does take off and land at the same height, or in general, some projectile motion. First of all, we want to remember that at max height, your velocity in the y is 0 meters per second. It goes up in the y direction, vertical direction. It stops to turn around for a split second, and then it starts falling back down. So at max height, here at max height, your velocity in the y direction is 0. We're going to be using this in this problem. The next thing is, don't forget that your velocity here, it's shot at an angle. You have a velocity initial in the x, and then you have an initial velocity in the y. All right, because this hypotenuse has a horizontal component and a vertical component. And we're going to remember one of the most important concepts in projectile motion is that the horizontal direction is completely independent from that vertical direction. All right, in other words, what's happening in one direction is not happening in the other direction. And the only thing they really have in common is time in air. One object, so it has to have one time in the air. All right, but in the x direction, it is just going east this whole time. And in the y direction, vertical, it's going up, it's stopping, and then coming down. Remember, there's no acceleration in the x direction, which means your velocity in the x stays constant. And not only constant, but if they give you this angle, which they will, or you're solving for it, then it's always cosine. That velocity in the x is cosine of that angle. So it's going to be v, meaning this whole velocity, hypotenuse, times cosine theta. And that's what your Vx is going to be the entire time, the velocity in that horizontal direction. All right, doesn't matter if you're over here, doesn't matter if you're here, doesn't matter if you're at the top. There's velocity in the x direction. Is there velocity in the y at max height? No, it's 0. All right, the other concept is if this takes off here with a velocity v and it takes off and lands at the same height, then this is velocity v as well. They're equal because acceleration doesn't change in the y. The acceleration in the y is negative 9.81 meters per second squared. It doesn't matter if you're going up or coming down. So if they take off and land, these velocities are equal. All right, perfect. And actually any velocity that is like directly across here are equal. All right, perfect, at the same height across. Now, I think that does it for this. So now we've had some good concepts that we're going to be using. So we're going to get started on this actual problem. We're going to ask for 4 things. Max height from the ground. Now, max height means here from the ground. This is what we're looking for, that delta y. Our final velocity not just in the y, not just in the x, but final velocity, this total final velocity here. And a lot of times students are like, oh, that's easy, it's 0, it hits the ground. Wish life could be that easy in physics, right? Actually, we stop the problem right before it hits the ground. So we're looking for that final velocity right before it hits the ground. Total time in air and how far it landed. Now again, back to our projectile here, time up equals time down if it takes off and lands at the same height. Here, time up will not equal time down. Okay, so here we go. Let's get started. We're going to use those big 3, also known as, well, they're really the UAM equations, but known as the big 3 in physics. And we're going to get started here. We want max height from the ground. Okay, I'm going to go in the y direction, in the vertical direction. And why do I do the vertical direction? Because I have this little secret extra information in the y direction. I know that at max height, my velocity in the y is 0. I also know that my acceleration in the y is negative 9.81 meters per second squared. So I've got a couple of little secret little secret information that I know that the problem hasn't given me. So I'm going to start in the Y direction, vertical. I know nothing about time at this point. So there's only one UAM that does not have time in it, and that is this equation. And I am using all my Y subscripts. Why? You don't want to accidentally plug something in from the horizontal direction, the X direction, into this. You can't mix them, they're independent from each other. So I'm gonna use those Y subscripts to keep it straight, and it's a really good habit to get into. All right, now I'm just gonna start looking at what I've got. First of all, you have to define where you're gonna use this in the problem. I am going to use this from where I start to my max height. So this is going to be from where it's shot to max height. You need to define the parameters in this problem of when you're going to use this. So that's when I'm going to use it. So my final velocity, if it's to max height, my final velocity is 0 at max height. My initial velocity is not 15. You can't plug in 15. I'm going to blow that up. This is 15 meters per second. This is an angle theta, which happens to be 42 degrees, and I'm looking for this Y component, all right, because only part of that 15 meters per second is in the vertical direction. Well, that is opposite that angle, that is sine. So if we said, hey, my initial velocity, well, here, let's start with sine theta, just to make sure we know this. Hopefully you're good at this by now, but let's go ahead and look at that. That's opposite, it's sine theta. The opposite is the initial velocity in the Y, and the hypotenuse is just your total velocity. So that's going to be velocity sine theta equals that initial velocity in the Y, and that means that whole thing in the hypotenuse. So I'm going to put that in, V sine theta for my Y. Do not forget to square it. Oh my lands, it's such a common error, and it's so frustrating. If you've got all of this analytical knowledge and you know how to apply it and you've got it right, but you forget to square, it's so frustrating. So remember that square. All right, acceleration of the Y is negative 9.81, and I'm solving for that delta Y. All right, we know, I'm gonna go ahead, here, let me actually just put A in here. All right, now I'm gonna put in some numbers. I've got 15 sine 42 squared plus 2 times negative 9.81. I got ahead of myself. I already multiplied the 2 in my head. Negative 9.81 times my delta Y. I'm looking for that delta Y. Okay, 15 sine 42 is actually 10.037. So that's going to be 10.037, but squared, plus that's negative 19.62 delta Y. All right, I'm going to subtract that over. The 10.037 squared equals negative 19.62 delta Y. All right, now I'm just dividing. I'm squaring this, dividing. I'm going to get a positive because my negatives cancel. And your delta Y is going to be 5.037. Okay, now here's the deal though. What is this delta Y? Is that really max height from the ground? You got to look at where you defined your problem from. We defined it from the start up here to delta Y. So that is actually 5.037 is actually this little height. Well, we want from ground. So if we take that height, 5.037, and we add it to this height, which is 5.3, we get our total height from the ground, which is going to be 10.337. That's a lot of sig figs. I would make that 10.3 personally. But anyway, for sig figs, because that's a lot. That's too many sig figs for me. So anyway, because we didn't even start with those kind of sig figs to know those numbers. So I would have called that 10.3 meters. Okay, perfect. Now that's max height from ground done. Now they want final velocity. Okay, we've got to remember, I'm going to blow it up over here. Final velocity is what they want. That's the hypotenuse. That means that there is a Y component, final velocity in the Y, and then there's an X component of velocity in the X, which by the way, we know, because velocity in the X stays constant. All right, and it is V cosine theta. And you're like, wait, what? Okay, so let's look at that again. We're going back to this triangle now. And remember, I'm going to write this a little smaller so you can, this side is velocity initial in the x. That is cosine to that angle. So if I do cosine theta equals that initial velocity in the x over that whole velocity of the hypotenuse, you're going to get v cosine theta equals that initial velocity in the x, or 15 cosine of 42. All right, now that doesn't ever change. It stays constant the whole time. That's that concept, because acceleration in the x is 0. If you're going to change your velocity, you have to have acceleration to change that velocity. Okay, perfect. So we know what this is. This is 15 cosine 42. But what we don't know is our final velocity in the y. But if we can find it, we can Pythag this thing. A squared plus b squared equals c squared. So we've got to find our final velocity in the y. I'm going to go right back to my, and I'm going to change colors here so we can see this. I'm going to go right back to this same equation where final velocity in the vertical direction squared equals initial velocity in the vertical direction squared plus 2 times my acceleration in the y delta y. And you're like, okay, why did you choose that? Because again, I don't know anything about time. So this is the only UAM I have without time in it. So this is the one I'm going to use. All right, but I've got to define the problem again. We're looking for that y component on this side. So I'm going to that velocity in the y from this side. I'm going to now define this from max height to the ground. So I'm going to redefine my parameters for this. And I'm going to call it from max height to the ground. Okay. So let's just start looking at this. Now, in this one, it was shot where it started here, shot out from something, to max height. So my final velocity was 0 because I was at max height. In this one, I'm starting at max height. So now my initial velocity in the y is 0 because it starts from rest and then starts falling and speeds up as it falls. So that's going to be 0. My acceleration in the y is negative 9.81. We know that. We know my delta y. If I'm going from max height to the ground, then my delta y is what I just solved for, this 10.337. All right, so I'm going to put the whole thing in here to get a little bit more accurate. All right, now what is my final velocity in the y though? That's what we're looking for, right? We said, hey, we want to find that so then we can Pythag this thing to figure out our total final velocity. So that's what I'm looking for. All right, well, I'm going to take, if you take 2 times negative 9.81 times 10.37, and then you take the square root of that, you get a final velocity in the y of 14.3785. Lots of sig figs. Now, that is also down, so we know that's going to be negative because that is falling down. Your negative won't necessarily come out here because you've got a negative, but if you try to take the square root of a negative, it's going to give you an error, right? So just know that that is negative, it's down. You need to put that in there because, look, if you try to go backwards and you square a negative times a negative is a positive. So that's why you're gonna have that issue. But just know that's down. Pay attention to what you're doing. Kind of think about this and go, oh yeah, this is falling down. That's a negative number. All right. Now, so I have final velocity in the y, but that's not what it asked for. It asked for the final velocity, the hypotenuse. So I know this is negative 14.3785. All right, just put some extra numbers in there and we'll clean that up and sig figs at the end. All right, so now all I do is Pythag this. I got my my final velocity in the y squared plus my velocity in the x squared equals my velocity squared final. That whole hypotenuse, this guy is what I'm looking for. All right, so here we go. We know that's negative 14.3785. Don't forget to square that. We know that my x is 15. Oh, I should have put that in here. Let me go ahead and put in. your final velocity, negative 14.3785 squared, plus that 15 cosine 42, because remember that does not change at all in the problem. And then if you square that, you're going to get a positive. You add that, because you're going to square this. You add that to 15 cosine 42 squared, and then you take the square root to get your final velocity. So your final velocity ends up being 18.19 meters per second. Now that is going to be a scalar value here. You're not going to have a negative because you have a positive in the x direction and a negative in the y. So that's just going to be showing you that this is the speed of it when it hits the ground. Okay, perfect. All right, hopefully you understood that. We're getting good at the math here, so I'm not going to waste your time showing you what this number is and adding it to this number, because remember, negative times a negative is positive, and then taking that square root. But that's what you're going to get for final velocity. All right, next thing it wanted was total time in air. All right, so I'm going to go ahead and erase this because we need some more room. We're going to erase this, and we're going to go with total time in air. Okay, the first thing I need is I'm going to do, again, I need my time. I'm going to do my first, I call it the first equation. It looks like this, and I'm going to do this all in the y. Why again? Why am I using the y? Is because I have these little two secret information pieces here that I can use. That my final velocity is, my velocity in the vertical direction is 0 at max height. So where am I going to do this from? Again, you've got to define where you're using this. I'm going to do it from the start again, from where it's shot to max height. All right, well, if I do that, here we go. I know my final velocity in the y is 0 because I'm going to max height. Here I started at max height, that's why it was 0. All right, my initial, we know that, it's 15 sine 42, or my velocity sine theta. All right, I know my acceleration is negative 9.81 t. I'm going to subtract that whole little expression, negative 15 sine 42. And where did I get that again? From right here. When I was looking at, you can't just put 15 in here, because on my initial velocity in the vertical direction, it was not all 15. Part of that was in the x, part of that was in the y. Equals negative 9.81 t, and I get a time. If you take 15 times sine of 42, divide by 9.81, because your negatives cancel, you get a time of 1.023. Okay? That's my time, but that's only my time from start to max height. If I want total time in air, I also need this time from max height all the way down to the ground. So now we're going to do it again, just like we did over here. We're going to use the same equation again, but now we're going to define it again differently. Plus AYT. We're going to define this from max height to the ground. When they take off and land at the same height, it's just time up equals time down. You can multiply by 2 and get the answer if you find time up. In this one, we cannot do that because it doesn't take off and land at the same time. It's going to be in the air longer on this side than it was here. Okay? All right. So, but now max height to the ground means that my initial velocity in the y is 0 because I'm now starting at max height where that velocity is 0. My final velocity in the y, we already found that. It was negative 14.3785. We found it right here when we use this equation. All right, and then I have plus my acceleration, which is negative 9.81 t. Now some students are like, why is this not v sine 42? Why isn't my final velocity here v sine 42? Because it fell longer. It speeded up as it fell. Right here, if you go directly across right here, your velocity in the y is 15 sine 42, but a negative because it's down, because it's in the y. All right, directly across. but it fell longer. It speeded up, and it was getting faster in the y direction as it fell longer. So that's why we had to use this formula to figure that out. All right, now I'm going to take I have this negative 14.3785 equals negative 9.81 t. I'm going to divide that, and I get that my t is 1.467. Okay, so that is time up. This is time down. If I want total time, I just add them up. All right, so my total time is going to be that 1.023 plus 1.467. It's going to give me 1.49 seconds. So look, check, check. Now all I have to know is how far it landed. This, we're going to use the big 3. And I'm going to use, I've already used the one with the squares. I've used the first one, I like to call it. We haven't used that third UAM, and I'm going to use that for this. So I'm going to make a little box here so we can see how to do this. All right, so we know that delta x equals that v naught in the xt plus 1/2 a xt squared. All right, so we look at this. Okay, first of all, there's no acceleration in the horizontal direction. Gravity does not work horizontal. It is pulling you down as far as we are concerned for this unit. So gravity is pulling you straight down. So this is 0. All right, so now my delta x equals my v naught x, which we know this, it's that 15 cosine 42. We're not putting the whole 15 in because only part of that was in that horizontal direction. And then we have, this was 2.49, sorry, woohoo. 2.49, let's get that right. All right, because it is 1.023 plus 1.467 equals 2.49, my bad. All right, so that's 2.49. All right, and now delta x equals 27.8 if you were to do that math. And again, I'm not going to really waste time in these videos. Now we're getting good where we can do this in our calculator. Take cosine 42 times 15 times 2.49. And now you know how far it went. And that would be from this distance here at the base of the cliff to where it landed. Would be 27.8 meters. Okay, that is a lot of things that they could ask for a projectile problem that starts and lands at a different height. Shout out again to that question. Great question. Thank you for sending that in. And if you like these videos and they're helping you, we would love for you to subscribe, share it with friends who if they need help, we would love that as well if they're helping you. And thank you for watching. Happy physicsing.